working at the chair of computing and engineering at Ruhr-Uni-Bochum. So I'm working on the university and not as most of the presentations we saw today in the business. I'm going to be speaking about simulation and mechanized tunneling. And first I would like to introduce a little bit the partners that are associated with this project. First of all, I'm working in the so-called Collaborative Research Center 837. This is a research center installed at the Ruhr-University in Bochum. There are several, 14 projects. I'm just one of these projects. And we're working on mechanized tunneling in particular. Then, of course, the Ruhr-University is to mention. Then Simplan AG Germany. I would like to thank Simplan AG especially for the technical support they're providing us. They're giving us advice in the creation of the model. Then we have a constructor of tunnel boring machines, is a German constructor. It's called Herrenknecht, and the Wehrhahnlinie in Düsseldorf. This is an ongoing project on mechanized tunneling. It's currently executed, and they are providing us with data for the simulation. So, tunneling projects. Probably not everyone is familiar with tunneling projects, so I just have here a few slides for your information. We are talking about really big diameters, normally ranging from 6 to 12 meters in diameter, but they can be over 19 meters, which then means that you have two levels of infrastructure through one tunnel. There's maybe cars going on the first one and trains are going on the second one, and then you have ventilation and installation and so on. The length is quite extreme sometimes. Normal length is, especially in urban areas, is so 1, 2, 3, 4, 5, 10 kilometers, sometimes 20 kilometers. But there are also tunnels that are over 50 kilometers long, and so you have a very, very long supply chain and a very long construction site. It's a very complex system for civil engineers to plan adequately. Just to give you an impression, when you have an excavation, you have a diameter of 10 meters, which is not too big, length of 15 kilometers. You're dealing with over 1 million of cubic meters of soil that must be excavated. So this is quite a huge amount of soil, and you really have to handle this, and it's not that easy at all. The machine can be quite heavy, more than 350 tons, 400, 500 tons is possible. And they're very strong actually, so 10,000 horsepower is also quite normal actually. Tunnel projects, there are numerous tunneling projects ongoing in the moment. A lot of them are in Europe. Asia is very active in tunneling. Singapore alone has the same amount of tunneling projects ongoing than Central Europe. This is quite impressive in my mind. USA, of course, and Russia. Actually, this one is a picture of a tunnel in St. Petersburg. They're digging in not horizontally, but with a certain degree, which is technically very, very complex. Speaking of costs, the whole project, including installation, including train rails, for example, frequently exceeds the €1 billion benchmark. So this is quite a lot. The machine alone is around 1/3 of the project, so 300 million is often. They must be constructed for, well, normally they are constructed for every single project. So you can't really reuse them often. Monetary losses due to insufficient supply chain, they are ranging around 20%. And imagine the machine has to wait for, say, an hour. The costs on the costs for 1 hour when the machine stops because there's material missing is from 2,000 to 5,000 euros. So when the machine is standing for more than 1 day, you reach 100,000 euros of losses just because there's no material on the job site. And this is, we are hoping that we can cut, well, if we can cut 5% there, this is impressive. So there are several techniques for tunnel construction. There's several techniques for unstable grounds, for stable grounds. I'm just going to show one that we're focusing on. This is a video I took from Herrnknecht. If somebody's interested, the full video is accessible on YouTube. It's like 12 minutes long. Mine is considerably shorter. So this is a machine applied in Spain. We have 12 meters of diameter, almost 100 meters long, so it's a very long machine. You see the turning cutting wheel. There's tools attached to this cutting wheel. This rotates, loosens the soil. The soil then enters into an excavation chamber where it's extracted from a screw conveyor. It's taken out there. It's then propagated to a conveyor belt. We see here a continuous flow of soil. After a certain length, excavation stops, and in the protection of the shield, there's a steel shield around the machine. In this protection, then the actual tunnel is installed. There's a ring installed there. Here we see the delivery of the rings. They're normally transported there by trains. Then they're unloaded by a crane. Here we see the installation by a so-called segment erector, which picks up the segment, puts it into place. Then the thrust checks fixate the segment. Then, ring is complete. After completion of ring build, excavation starts again. Excavation stops after a certain length. You build another ring, and I think you get the idea. So this is a cyclic alternation of these two core processes. So we are working on a process simulation in mechanized tunneling, and when we're talking about processes in mechanized tunneling, we use a certain classification. I showed you the first two core processes, advanced and ring build. They are influenced by their support processes, as inspection, maintenance. So this is a downtime. We know when this is going to be happening and how long this normally takes. We have a support. We have support processes that are coming from the supply chain. Supply chain is divided into four pillars. As the backup system right behind the machine, we have segments, grouts, pumps, air ventilation is installed there and stuff like that. We have the tunnel itself, where we have normally a belt conveyor or the rails or the passages of rails when you have several trains going in and out at the same time. We have the subsurface job site, where you have a separation plant, concrete plant, and management containers, and so on. This must be taken into account, of course, and the external logistics is very important, because when you're working in urban areas, for example, you don't have the space available to create the rings or the segments, the concrete rings. You just build them somewhere else, maybe 400 or 500 kilometers away, and then they're transported to the job site. And all this system is highly influenced by so-called unplanned downtime. They're resulting out of several conditions or out of several reasons. We have very difficult ground conditions sometimes. There's water ingress, you have unstable conditions, you have settlements, you have structures that cannot be damaged, like the Colosseum in Rome. When they're tunneling under there, you don't want to damage this. We have wear and tear, technical interruptions, organizational interruptions, lack of capacity, and all this really influences the system. And we are focusing on how does this influence the project itself? How does it slow down the project? So we're decomposing this system of mechanized tunneling into three big parts, actually. And one is the advanced, the ring build, and the supply chain. And I'm going to be talking a little bit about how we actually did this. So I'm going to be starting with the advance. This is a screenshot from AnyLogic, top level of our simulation model. We created all the assembly parts of the machine, like all the machine components as active object classes. And this red frame indicates that these parts are responsible for the advancement, for the excavation. And you see here there's a continuous propagation of material between these three segments, and we are using a multi-method approach there. So we are simulating the processes with discrete event simulation, and the material flow of the soil you saw in the video with system dynamics. And for your information, we are also considering technical disturbances, and we are estimating the time between two failures, also mean time between failure, and the mean time to repair them by probability distributions. I have another video that should show you the multi-method approach. We have here the process and here the material flow handling. So when excavation is activated, this triggers the material flow with system dynamics. Then a certain amount of soil must be excavated. You have a certain excavation rate, which results from the speed and the diameter and the swelling factor of the soil as well. Then ring build starts. You don't see anything here anymore. Then after ring build, this will trigger again the process of excavating. Then the system dynamics starts again when this is finished, and so I think you get the idea. I'm going to be fast forwarding this, I hope. Oh yeah. Okay, so here you see a 3D animation of the progress. Now we have a disturbance. The machine itself, or the cutting wheel itself, is disturbed. For example, hydraulics break down. And after fault remedy, this continues again. Now something else is disturbed. Maybe another element that this element depends on. So maybe a pump is disturbed or something, or we don't have grout. So we're dividing, is really the element there, the element itself disturbed, or is something else along the path what this element is depending on, is this disturbed? Okay. Yeah. So second part is the ring build, which is mainly simulated with only one component, is the erector. It's a screenshot of internal setup. I think I don't have to really explain that to you. Most of you know. It's just a process simulation. We don't have any continuous material handling there, so we don't use system dynamics in this one. We have, so far, we have only established a simulation component for the delivery system. So we're working on the backup system and the subsurface job site at the moment, but this is only the presentation of the current status of this project. So I'm just going to show the delivery system, which is simulated with the help of the rail library, and then in the class for tunnel train. We're using the rail library there, and also, of course, enterprise elements from the enterprise library. We have the delivery of segments to the job site there. They're stored in somewhere on the job site in the storage. The creation of the train, then the train goes via a certain infrastructure to a loading position where there's a portal crane picking up segments, putting it on to the train. Then the train goes into the tunnel, reaches the back of the machine where it's unloaded, and then the train can go out and be reloaded again. So I think it's very self-explaining to you. Short case study. It's an artificial case study actually to show some results we can generate with this model. We have 4 different layers of soil that must be passed to construct this tunnel. The tunnel totally has a length of 8,000 meters. Diameter of machine is 10. Each segment is 2 meters wide or long, depending on which way you look at it. So actually you have to construct 4,000 rings to build a complete tunnel. And the segments per ring are 7, or in tunnel language you have 6 plus 1, which means you have 6 normal segments and 1 key segment to really fixate the ring itself. We're considering technical disturbances. As I said earlier, this is an example for the main drive. For example, mean time between failures, minimum 50, maximum 450 hours. So at least after 450 hours, the machine, the main drive, the component main drive, breaks down at least once. And depending on what's happened, if there's an electrical disturbance or if some some pumps or some pipes have to be exchanged. The mean time between failure varies from 2 hours up to 50 hours. So 2 hours if you just have to locate the electrician up on the job site, subsurface, and bring him to the machine so you can figure out what is the problem, or if you need to really order a new component that must be installed there to repair and finish troubleshooting. Input data, we have in this research, in this collaborative research center, one of the projects is focusing on a product model for the tunnel boring machine and for the subsoil, and we connected to them. So we have a database, and we just take out the properties and the values of these properties to parameterize our system. The same we do for the soil. We have a model of the soil, and we assume that each soil layer allows a certain speed of excavation with this minimum and maximum, as I showed for the technical disturbances, pretty much the same idea. We just use a triangular distribution to generate these values. We started with connecting into Excel and just taking out the values from Excel. When we run the simulation, we can already produce some good results. The main performance indicator in mechanized tunneling is the daily advance rate. Means how many rings do you assemble per day? Here on the x-axis you have the days. So this project took a little bit more than 1 year. You very clearly see the different soil layers. So in the first soil layer you could excavate really fast. This means you have enough time you have more time to build the rings. Second layer was even faster. You could spend more time on the ring build itself. Third layer was a little bit difficult to drill, so the excavation took much longer and took away time from the ring build. What we also see very nice is the impact of the disturbances, where the performance goes down. We have standstills, and we have sometimes really high increases of the performance there. Analyzing the disturbances, I plot here a timeshare of the total project. So you see the time for the advance, the time for the ring build, technical disturbances, and technical disturbances can be broken up into the reasons, which element was really disturbed at the moment. So you see here, for example, the main drive was disturbed for 34 days, which is really a lot. You should think of a backup system there, maybe. Analyzing the missing resources, the production couldn't go on for 11 and a half days, because segments were not delivered in time. They were actually ready to start the ring build, but there was nothing to build the ring with, so they had to wait. And the same is true for grout, for the mortar that is pressed during excavation to prevent settlements. They control the settlements and stabilize the machine and the ground with mortar. And excavation is only possible if there's mortar available that can be pressed into the ground itself. So no mortar, no excavation. They had to wait for another 4.5 days. So what we see is that the supply chain really slows the project itself by a considerably amount of time. Summing up the current status of the model, we are using alternating soil conditions. The dimensions of the machine and the tunnel are regarded. Process duration is put into the model, probability of disturbances, and the typical consumption of resources. Results we gather at the moment is, of course, the duration of the time and the impact of the disturbances, daily advance rate, as I showed you earlier. We would like to provide more information for the civil engineers on the job site for logistical weak spots, so they could actually adopt their system and optimize, or at least shorten the waiting because of missing resources. We can see that sometimes the machine can go very fast, but the supply chain itself has a limitation. And we would like to find out what is the limitation, the logistical maximum that we can go for one day. And we would like to give information about the short-time consumption of resources, so how to allocate resources, when to order them, or when to create them. And as an outlook, okay, something is missing here, sorry. We are considering the soil conditions. We created a simulation model for the shield machine. The delivery with the train is established as well, and we're working on a backup system, external logistics, subsurface job site, and uncertainties resulting from the soil. For example, they must be taken into account as well into a model. And finally, we're gonna validate the simulation model with data provided by the Wehrhahnlinie in Düsseldorf, as I mentioned earlier. So this is a new subway they're constructing at the moment through the city of Düsseldorf. And we are taking measurements there, and we are collecting data there to validate our model in the future. So thank you for your attention, and if you have any questions, I'd be glad to answer.